In this video, we'll first start to look at polar reactions and learn how to write their mechanisms. When we think about a polar reaction, that's where we have an unsymmetrical distribution of electrons. And if we think about a polar compound and a polar bond, let's say we had methanol. And if we remember back to our general chemistry and remember about dipole moments and figuring out if molecules have an overall dipole or not, we can start to guess if they're polar molecules or not. And so molecules with an unsymmetrical electron distribution are polar. So this causes bond polarity. And remember our electronegativity, the oxygen here wants electrons a lot more than that carbon. So the electron distribution is going to go from the carbon up towards the oxygen. So the oxygen is going to have a lot of electron density around it. The carbon, not so much. So our oxygen is going to be a partially negative charge, and our carbon is a partially positive charge. Because the bonds in some functional groups are polar like this, that's how we start to get polar reactions. And so since that carbon atom has a slightly partial positive charge, something with a lot of electrons, let's say we have a bromine with a negative charge, that bromide ion, that can come and attack the positive charge. So that bromide ion comes and acts as a nucleophile or Lewis base and attacks the carbon, which is our electrophile or Lewis acid. And it can do that because of the polarity between the carbon and oxygen bond, since the oxygen is much more electronegative. Carbon atoms can also be partially negative. So if we have a carbon atom bonded to a metal, examples if we had it bonded to magnesium, we'll see these later on. They're called Grignard reagents. But in a Grignard reagent, since that carbon is bonded to a metal, the carbon's actually partially negative and the metal has a partial positive. So depending on what our carbon atom is bonded to, it can either have a partial positive charge if it's bonded to an electronegative atom. If it's bonded to a metal, it tends to have a partial positive charge. So it's this unequal distribution of electrons in the molecule that allows us to do polar reactions. Before we get into the actual reactions and mechanisms, I want to get into a couple more definitions. First, we're going to look at polarizability. Polarizability is the tendency of an atom in a molecule to undergo polarization. Large atoms are easily polarizable. Small atoms, not so easily. If you think about your intermolecular forces, if you had two fluorine atoms and they're right next to each other, that fluorine atom is really, really tiny. You can't move the electrons around that much on a small fluorine atom. But on a big, giant iodine, there's lots of space there. You can kind of squish it around. It'd be the same idea as if you're trying to squish a softball. The fluorine would be the softball. They're really hard to squish versus a beach ball, like the iodine. With the iodine, you can kind of squish that beach ball much easier. With that iodine or beach ball, you can squish it a lot easier than you can squish the fluorine, which is more like the softball or baseball. That's the idea behind polarizability. If you can squish it and it's really big and it takes up a lot of space, I can move the electrons more to one side or the other. So here I can end up with an iodine being slightly partially positive on one side, slightly partially positive on the other side. And then they'll start lining up like that. So that means when we're looking at a carbon with a sulfur versus a carbon with an iodine, since the iodine is a larger atom, it's more polarizable. The sulfur, not as polarizable. And a quick review of nucleophile and electrophile. Remember, nucleophiles are the electron-rich species. They're the ones that donate the electron pair. So they're the ones that do the attacking. They're the Lewis base. The electrophile, those are the ones that contain either that positive charge or partial positive charge. Those are the substances that accept the electron pair from the nucleophile. They're your Lewis acids. So the nucleophile, that's your Lewis base. That one is where you start your arrow. And your arrow points to where it's going, to where those electrons are going. So the arrow always starts with the nucleophile and points to the electrophile, because that's the one that's giving up the electrons to make the bond. And one last definition, carbocations. So for polar reactions, they occur by the combination of an electron-rich site and an electron-deficient site. They occur by combining a nucleophile and an electrophile. Carbocations are substances that are trivalent and positively charged carbons. So they have 6 electrons. And so you may hear it get referred to quite often. When you draw a carbon that has a positive charge, it tends to get called a carbocation. Let's look at a mechanism for a polar reaction. So I showed you guys this one before. I'm going to show it to you again. Here we have our double bond. It's the nucleophile. It does the attacking. Since the HBr is a very polar bond, hydrogen is partially positive, bromine is partially negative, because bromine is more electronegative than hydrogen. So that double bond is going to take its electrons and attack the hydrogen, which then moves electrons onto the bromine. This then creates our carbocation. And our bromide ion. So here we have our carbocation. This carbon down here went from having 2, 4, 6, hydrogen makes 8, to now only having 6, 2, 4, 6 electrons. So we went from an octet to now we have an unfilled octet. We have a trivalent carbon here. So what'll happen, the carbocation is not a stable configuration. So the bromine with its extra electrons will come and attack that very electron deficient site. This then creates our product. So sometimes mechanisms are short like this, where it's a couple steps. Other times you'll start to find mechanisms can become longer. But either way, just keep following the electron flow. Always think about where your nucleophile and electrophile are and what the next step would be to try and get towards your product. And then one final note, when we're looking at polar reactions, we can draw reaction diagrams. So you've seen stuff like this in your general chemistry. With organic chemistry, here we have our reactants that we start with. They'll go through and create that first reaction. Here we have the carbocation. So remember, that's where we have our trivalent carbon. That's our carbocation, is our intermediate here. Then we have our transition state going to our product. The two transition states here, that's when the bond is being formed and broken. So that's when we have our partial bonds. So if we go back to our reaction and we go back to our mechanism, those transition states, that would be where the double bond is starting to break, so it's not a full double bond anymore. The bond to the hydrogen is starting to form, and the bond to the bromine is starting to break. So all of these are dashed lines because they're not full bonds. And usually when we have a transition state, we put inside brackets and do a double dagger right outside the bracket to indicate transition state. And so we can even create a transition state for our second step. So that second hill on our reaction diagram will be where the bromine is starting to make that bond with our ring. So if we look at what we've drawn here, and we want to number it, step 1, 2, 3, 4, and 5. We've drawn 5 different stages of the reaction. On our reaction diagram, here we have 1, 2, 3, 4, 5. So each one of these transition states is represented by my drawing in red inside the brackets with a double dagger. An important thing to note, you can never isolate a transition state. Transition states are not isolatable. We can't see a transition state. We can theorize it, but we can't see it. The intermediate, we have a possibility of actually seeing an intermediate through advanced technology. But transition states, they don't last long enough for us to actually see them. And that's because that's when the bonds are in the middle of being made and broken. And so now you should know a little more about polar reactions, which we'll be seeing a lot throughout this class, and know how to start drawing mechanisms. Remember to think of it in terms of your nucleophiles and electrophiles, and draw the full head arrow. Draw the full arrow to indicate that it's 2 electrons that are moving at the same time.